I wanted to record a quick video or two going through these problems that I gave for extra credit. We started in class solving the problem that's in the box, dealing with some lemonade and some ice and determining that the final temperature of the lemonade after the ice melts was 18.6 degrees Celsius with this small cube of ice. Then we extended that problem and said, okay, let's say that we wanted to have 20 grams of ice remaining in the punch bowl in the final equilibrium state. Having ice and liquid together in the final state at the same time means that our final temperature is 0 degrees. So we want to know how much ice, that's the first thing we're going to talk about, how much ice do we need to add to our initial lemonade at room temperature, 20 degrees Celsius, in order to achieve that state. So we have to think about, well, what is going to happen with these objects that we have? We have some lemonade and we have some ice. We know the lemonade is going to lose temperature from its initial temperature to 0 degrees. And we know the ice is going to warm up and then partially melt in this problem. Not completely melt and then warm up further, like we had in the problem class, but partially melt. So let's first ask ourselves, well, what energy do we have available? What energy do we have to work with to do something to our ice? Well, we know the energy that the ice gets in order to melt, to increase temperature and then to melt, comes from the lemonade cooling down. So we can say that the energy available is going to be mc delta T for the lemonade. So we say, okay, the mass of our lemonade is 3.95 kilograms. We're treating the lemonade as water, 4186 joules per kilogram Kelvin. And then the lemonade undergoes a temperature change of 20 degrees Celsius. So I'm being sloppy with my signs of my temperature change because this is the energy that the lemonade gives up. So really we should say minus 20 degrees. And this tells me that I have minus 3.307 times 10 to the 5th joules of energy available. That's the energy that the water, or the lemonade, must give up by decreasing its temperature 20 degrees to go from the initial state of room temperature down to the final temperature of 0 degrees. So where does that energy go? Well, then that means that that energy goes into the ice. So I could then write an equation saying that 3.307 times 10 to the 5th joules is going to equal mass of my ice times the specific heat of ice times the temperature change that the ice undergoes as it warms up, plus the mass of my melting ice times the latent heat of fusion. Now the mass of my melting ice is not equal to this because our problem statement specified that I have 20 grams left in the equilibrium situation, which means I have more than 20 grams of ice to begin with. So I'm going to say that the mass of ice that I start with, I'm just going to call it Mi. The specific heat of ice is given as, let me just check over here, 2100 joules per kilogram Kelvin. The ice undergoes a temperature change of 3 degrees. It started at minus 3 from the freezer and warms up to 0 degrees before it starts to change phase. And then this mass of my melting, I can express that as the amount of ice that melts is the initial amount minus what I said I wanted to have left over, 0.02 kilograms, multiplied by the latent heat of fusion, which is, I hate the word wrap these, but I'm always so lazy about how I manage my space, 3.33 times 10 to the 5th joules per kilogram. So again, just to be clear, because whenever I wrap, that is equal to that. So this term, it shares two lines, so just be careful with that. Solving that, a little bit of extra work, gives me a mass of my ice that I need in order to have this of 0.994 kilograms, just about 1 kilogram of ice. I started with about 4 kilograms of water. That's about 4 liters of water. This, your typical average size beaker here, it says 400 milliliters to capacity. So that's, filling it up to the brim, not up to the brim, but here. So about twice this volume of ice. So a big block of ice dunked into that room temperature lemonade will give me that perfect 0 degree with just a little bit of ice remaining. In the next video, we'll do the next problem, but I want to keep these kind of short.